Welcome all. Today we are going to deal with the topic an introduction to knot theory, a topic that is not that much familiar to us but is still under progress. It falls under the branch of topology, and this session deals with what is a mathematical knot, different types of knots, their projections, and how to distinguish between equivalent as well as different knots. And it briefly gives an idea about classical knot invariants. So let's begin the session. Now, speaking about notes, these notes are not that different from the notes we're familiar with. The only difference is that these kind of notes don't have loose ends. And once you tie it, you can't untangle it without using scissors. So, basically, to get an idea, we shall think like this that let's take a string and glue it such that it has no loose ends. Then you get something that is similar to a mathematical note. So, you can briefly say that a knot is a closed curve that do not intersect itself anywhere. And knot is something that lies in space. So you can say it's a homeomorphism of unit circle in three-dimensional space R cube. Now we deal with different types of knots. The simplest of all knots is called a trivial knot or unknot. That is something that you can view as a circle or better say a ring. Then the other common knots that we can say is overhand knot, which is also known as trefoil knot or clover leaf. And the other one famous is that figure eight knot, which is also known as four knot. Trefoil and figure eight knots are something that you come across when you study the basics of knot theory. Now, a polygonal knot is a knot which is a union of finite number of closed line segments joining vertices, something that you can just compare with a graph. Now we can say that there are different types of notes that you come across as you study mathematical notes. A few are listed below. This figure gives an idea about what a mathematical note is, and the first column depicts the notes that we just found out. They are unknot, trefoil knot, and figure eight knot, and there is plenty of notes that you can find as you move forward. Now we speak about a basic as well as an important topic in studying different types of knots. As I mentioned earlier, knots are situated in space, that is in R cube. So in order to study these knots in R cube, we study different projections of knot in plane. So the mapping that brings a knot in space to a projection in plane is called a parallel projection. It is a mapping from R cube to R cube. And if K is a knot and K dash is a projection, K dash must be an image of K under parallel projection. If you observe the figure situated along with this, you can say that a trefoil knot has more than one projection. You can project a knot to XY plane or YZ plane or XZ plane. It doesn't matter, it gives you different projections. So from here you can conclude that a knot can have more than one projection as the parallel projection, but the function changes. Now we speak about double point. A double point of projection. Before speaking about double point, you must be clear. At the very beginning of the introduction of notes, I had stated that notes don't intersect itself. But though the notes don't intersect itself, its projections may seem that they intersect itself. It's just because an under strand and over strand made together gives you an image of having a crossing. Just if you observe the image attached with the slide, you can see that it gives such an impression. So, in order to show that there is an overstrand as well as an understrand, while drawing a regular projection, you denote a double point by giving a cut. Such a diagram is called a regular diagram. And as we observed before, a particular node can have more than one regular diagram. And this is an example of figure 8 node. You can see three different projections, regular diagrams of figure 8 node. And if you observe closely, you can see cuts in between. These cuts denote the actual double crossings or double points in the node. Now we speak about different general types of nodes, that is like alternating nodes, oriented nodes, etc. And if you speak about alternating nodes, you can say that it has a projection that has crossings that alternate between over and under as one travels around the node in a fixed direction. So if you depict it, you can see that here this node, particular node projection, it begins from an under crossing, but it moves as an over strand, as you see, till it reaches some double points. And once it reaches the double point, you can see that it begins to move as an under strand till it reaches some other double point. From there, it again begins, it alternates to become an over strand, then it alternates to give you an understand strand. Again, it moves as an over strand, then shifts to an under strand, again to an over strand, and it stops. As you move in a particular direction, you can see the knot is alternating, it's over crossing and over strands and under strands. So this is what we basically speak about alternating notes. Now we speak about composition of notes. The basic idea of composition of knot is that you can obtain a new knot if you're given two different projections of knots. It is obtained by removing a small arc from each knot projection and connecting the four endpoints uh, by two new arcs such that they do not have any crossings in between. So the resulting knot would be called the composition of knots. And if J and K are two knots, their composition is denoted by J hash K. Uh, and in figure, if you observe, you can say that there is a projection J and there is a projection K. You can give an idea that this particular part of J and a small portion near it, such that they do not intersect, okay? This part of K are removed. So you can see it is depicted by dotted lines, and that four endpoints are connected by a new knot, a small arcs to give a different knot called composition of knots. Now, a composite knot is a knot that can be expressed as the composition of two non-trivial knots. Just in front, as we begin discussing the composition of knots, the image that attached with the description was a composite knot because it can be expressed as a composition of two non-trivial knots. And just like we speak in multiplication, that is any number multiplied by 1 gives the same number. Composition of any knot with trivial knot gives the same knot, and it is depicted just above. If you take composition of any knot that with unknot, you'll get an image such that the particular knot that we considered is stretched a bit, but it is equivalent to the same knot. And a prime knot is just the opposite of composite knot, that it cannot be expressed as the composition of any two non-trivial knots. Trefoil knots and figure eight knots are prime knots. Now we speak about oriented knots. Oriented knots, just as the title suggests, is nothing but a knot with orientation. That orientation is depicted with an arrow in the projection. If you are given two knots, you can easily speak about two different orientations that the knot can possess. One is to move clockwise from a particular point, and the other is to move anti-clockwise. Now we speak about equivalent knots. If two nodes K and J are said to be equivalent, one node is transformed into another through Ready-Master moves. You would learn what is Ready-Master move as we progress. If you observe here, two examples are given such that both the nodes are equivalent, although it may not be the same, exact same as you see them and if you observe. The next topic is the core of studying node theory. It is Ready-Master moves. A Ready-Master move is one of the three ways you can change a projection of node, but it does not change the node. So it has a great importance and play a very big role in studying different nodes. It helps us distinguish between equivalent nodes, how to transform one node to another through Ready-Master moves. There are three Ready-Master moves: first Ready-Master move, second Ready-Master move, and third Ready-Master moves. First Ready-Master move allows us to put in or take out a twist in the node. Let's as the figure depths. The second Ready-Master move allows us either to add two crossing or remove two crossing. The last and the third Ready-Master move allow us to slide a strand of knot from one side of the crossing to the other. These are the three different Ready-Master moves. They are of very great importance in studying knot theory. Now we move on to knot invariant. A knot invariant is basically a function from set of all knots to any other set, such that the function does not change as the knot is changed. Or in very simple language, you can say that a knot invariant always assigns the same value to equivalent knots. But you should also note that the converse need not be true. That is, two equivalent knots possess the same knot invariant, but two knots that possess same knot invariant need not be equivalent. And the important part is that a knot invariant must be unchanged under Ready-Master move. You can see different types of knot invariants, and in this session we deal with a few classical knot invariants like tricolorability, linking number, crossing number, unknotting number, and you can find a bit more like bridge number, etc. Now we are going to introduce ourselves to different classical knot invariants. To begin with, we speak about tricolorability, a projection of a knot or link. Link is nothing but it can be, in easy words, you can say it is a combination of more than one knot. So a projection of a knot or link is tricolorable if each of the strand in the projection can be colored one of the three colors, so that the crossing at each crossing either three different colors come together or all the same colors come together. That is, if you are given a note, you can verify whether it's tricolorable or not by just trying to color it with such a way that at each crossing either three different colors should come together or all the same colors come together, provided you use at least two colors. If you don't use at least two, you can color any note with single color. So that's not the idea of tricolorability. Out of the three colors, you should use at least two colors, and the coloring should be such that at each crossing either three different colors come together or same colors come together. If this is possible in any projection, you can say that that projection is tricolorable. And the best example of a tricolorable knot is trefoil knot. Given two different projections of trefoil knots, and you can see they are tricolorable. In the first tricoloration, if you observe, at any crossing, you see that three different colors come together. But in the second projection, you can observe at certain crossings, three different colors come together, and at certain crossing, a single color can be observed in a crossing. Now we try to say that unknot and figure eight knots are different from trefoil knot. This can be observed using tricolorability. Unknot just requires one color to color itself. So you cannot say unknot is tricolorable because, as we mentioned before, in order to say whether a knot is tricolorable or not, you need to use at least two colors. So a knot is not tricolorable, so it is entirely different from a trefoil knot. And now figure eight knot, it requires at least four colors to color the knot completely. So it violated the tricolorability property. So it is not tricolorable. So figure eight knot is also different from trefoil knot. Or you can say unknot and figure eight knots are not equivalent to any tricolorable knots. The next section or the next knot invariant is a crossing number. A crossing number of a knot is the smallest number of crossing in any diagram of knot. That is, we've already discussed that a particular knot has more than one projection. So you try to find out the crossing number of each projection, say ck dash. And after finding all the crossing numbers of different projections, you take the minimum among the crossing numbers of projection. And that minimum is considered as crossing number of a knot. It is denoted by C of k, and the attached table gives you different crossing number. That is, an unknot has 0 crossing number, trefoil has 3, whereas figure 8 has 4. And observe that no non-trivial knot have crossing number 1 or 2. If you observe, there are 2 possibilities with crossing number 1 and 4 possibilities with crossing number 2. Applying the first reduced move, that is to take out a twist, you can see that there are knots. So no non-trivial knot has crossing number 1 or 2. So the minimum crossing number that a non-trivial knot can possess is 3. And if you observe the table, you can see that number of crossings with a particular number increases rapidly as the crossing number is increased. Now it is an example to how to find different projections. We take the example of figure 8 knot. There are 3 projections of figure 8 knot given above. So the first and second projection have crossing number 4, whereas the third has 5. But we've mentioned that crossing number of a knot is the minimum of different crossing numbers of different projections. So the crossing number of figure 8 knot is 4. The third knot invariant that we deals with is a knotting number. A knot K has a knotting number n if there exists a projection of knot such that changing n crossings in the projection would give you an unknot. And there is no projection such that fewer number, that is no projection that would give you an unknot if you try to change the crossings less than n times at n places, and you denote a knotting number of a knot by u of k. In the given figure, if you observe that the marked portion, if you change the crossing in the marked portion, you'd get a projection that is equivalent to unknot. So the unknotting number of the given example or the given projection is 1. Now we've listed different knots with their unknotting numbers. Trefoil has unknotting number 1. Figure 8 has unknotting number 1. So you can see that though trefoil and figure 8 are different knots, they possess the same knot invariant value for unknotting number. So just because the knot invariant value is same, you cannot claim that the knots are same or equivalent. They're not equivalent knots as if observed in tricolorability. Now next we speak about link. I've just mentioned it above in a brief way. A link is collection of knots that do not intersect each other but they are linked together. So A knot is also a link with one component. You can see different links made with unknots. You can consider other knots as well, but the easiest links are given above. You can see a link with three components, with two components, and with one component. If two knots are equivalent, they must have equal number of components, and you should be able to get one knot, one link from other by trying out some ready-made demo. And there is a question, that is, just because the number of components are same, does it guarantee that the nodes are the same or links are the same? If you observe Hope link and two unknowns, you can see that in appearance it might give me an impression that they are equal, but it is not. This property is given by splittable link. That is, a link is called splittable if you can embed a plane such that it separates one or more components of L from other component of L, link L, and the plane is disjoint from L. Otherwise, the L is said to be non-splittable. Hope link is non-splittable, whereas two-component non-trivial link is splittable. The fourth not invariant is linking number. A linking number is denoted by Lk of Kj, where K and J are the components, and linking number of a link Kj is given by sum of the signs of two crossing points of a diagram for Kj at which K crosses over J. Self-intersection of components is not considered while calculating the linking number. So there is an easy algorithm to compute the linking number. That is, if you have to rotate over strand in counterclockwise to match understrand, you give +1 sign, whereas -1 is given if overstrand has to rotate clockwise to match the understrand. Now there is a pictorial representation of the above mentioned algorithm, how to calculate sign of crossing number. And if linking number L with components k1, k2, etc. kn with crossings c1, c2, etc. cn is given by L equal to half of sin c1 plus sin c2 plus etc. plus sin cn. Now there is a depiction of how to calculate a linking number, and this easily gives a value about how to give the linking number. First of all, you have to orient the node in order to get linking number. Otherwise, you cannot say, or you cannot use the algorithm of giving +1 and -1, because you use the algorithm as to which direction the overstrand has to rotate to match the understrand. And if you see the above diagram or the given projection, you can get a good idea about how to calculate linking number. Now we've reached the conclusion of our discussion. These are only few knot invariants because there are plenty, and this topic is under research. It is still growing. So any equivalent knots have same knot invariance, whereas same knot invariance need not ensure that the knots are equivalent. And this particular branch of mathematics have wide applications, especially in genetics, in DNA synthesis and all, in recombinations as well. And because you can consider a circular DNA as something like a knot, and also in chemistry, in synthesis of chemicals, because certain atoms, if you're given different atoms, you can join them in more than one way. Joining in one way would give you some chemical, or you can say if you're synthesizing some medicine or something, and it might have certain after effects, and joining them in some other way might give you some knots with fewer or say better results and less after effects. So with this we come to the conclusion of discussion. Thank you.